Hello and welcome. In this video, we're going to be talking about how to find the area between equations that are actually not functions of x, but they're equations in terms of y. Then we're going to talk about what happens if we have curves that intersect to form multiple areas. How do we find the area between curves if there are multiple pieces of area? So let's jump right in. So let's start by considering this graph here and the shaded area A. Now, if I asked you what we talked about in the last video, what function is on top, because really what we want to do is find where these two functions are crossing, figure out which is on the top and which is on the bottom, so that we can set up our integral to find the area. So which function is on top? Is that clear? And I think the answer to that question is no. If someone asked me where the top of this area is, I would probably point to this point right here, but I don't know if this is the top or if this is the top, and that makes it a little confusing to try and talk about the area from top to bottom. What I want you to do is look at these two functions here, look at these two equations here. What do you notice that's different about them than everything that we've been doing before? And I'm hoping that what you notice is that they are in terms of y, and I shouldn't actually say that they're functions since they don't pass the vertical line test. They are equations in terms of y. So could we set this up as an integral with respect to y? So we're thinking, is there a way that instead of having a dx at the end, since our variables are in terms of y, could we write this as an integral in terms of y? Well, when we did this in terms of x, the first thing that we talked about was finding the bounds, which we can see pretty clearly from this graph. This point is -1, -2, and this point over here is 2, 1. Now, everything needs to be in terms about y. It's all about y right now. So if I look at the y values, my y values are -2 and 1. So -2 is smaller, that's going to be my bottom limit, and 1 is larger, that's going to be my top. Now, big minus smaller, top minus bottom, it's hard to tell what that is, which is what led us to this whole idea of noticing that it was about y instead of x anyways. So my tip to you is, instead of thinking top to bottom, if we're talking about y area, think right to left, or think right minus left. If I asked you which area is further to the right or which curve is further to the right, that is a question you could answer, and it's this quadratic piece. So -y² plus 3y. Nope, just plus 3. And which curve is further to the left then would be the line, so minus y plus 1. Why don't you go ahead and pause the video. I'm going to simplify this first. This is going to be -y² minus y plus 2 dy. Go ahead and pause the video and work through the integration on your own, and then unpause the video and see how you did. So if we find the antiderivative, we get this, and then if we evaluate it at 1 and -2, we get here, and then if we simplify those fractions, we get here. Okay, so pause the video if you need to check through your work there. If you're making fraction mistake work, that's less of a concern than if you're having issues with your integration. Let's go ahead and look at another example. All right, I would like you to pause the video and try and set this integral up on your own. So key things to remember, you can probably identify the bounds from the graph. It is a function of y, so when you identify those bounds, pay attention to the y values. And then when you're thinking which function minus which other function, you're thinking right minus left. So go ahead and pause the video and set up this integral on your own. So hopefully you had time to look at this. Our bounds are going to be y equals 0 and y equals 2. This is going to be a function with respect to y. And if I look from right to left, I'm going to have the line minus the quadratic. And remember, if for some reason you can't tell, you could always plug in a number between 0 and 2 to test which function is larger. Okay, so if I integrate this, I'm going to get y squared minus y to the third over 3 from 0 to 2. And if I plug in 2, I'm going to get 4 minus 8/3. And then if I plug in 0, I get 0. And if I find a common denominator, I'm going to get 4/3 units squared. All right, we're going to build on this a little bit and talk about what happens if we have multiple pieces of area. All right, here we have a graph of a cubic function in terms of x and a quadratic function in terms of x, but there's actually two areas being formed. And I'm going to talk about them as areas A and B so that it's a little easier for us to think through this. So we have been using one integral to find the area between two curves. So how many integrals do you think we're going to need now? That's right, we're going to do two different integrals. The process is really the same. If you can tell from the graph where those two are crossing, that's great. For me, I can see pretty clearly a couple of them, but I just want to remind you how to do this by hand in case you can't see the bounds. Set the two functions equal to each other. Get everything on one side. We're going to solve a quadratic here, and we're going to get 0 and plus or minus 2 as our intersections. So thinking about this as our area, we're going to have two integrals. The first integral is going to go from the smallest to the middle bound, and the second from the middle to the second bound. Now we need to figure out what's going on with our integrand. And let's talk about for area A first. Which function is on top for area A? 3x cubed minus x squared minus 10x. And which one's on the bottom? Negative x squared plus 2x. So we're going to subtract those. And if we distribute the negative and combine like terms here, we're going to end up with 3x cubed minus 12x. So that's going to be this area here. Now, one of the things that we talked about in the last video was that if we accidentally have the wrong function on top, the issue with our final answer is just going to be off by a sign. So if we accidentally had the quadratic minus the cubic, our answer would be negative. Well, in this second piece here, this second piece of area, the quadratic is forming the top of the area. So all we need to do is take the same two functions we just subtracted and change their sign. And you would get this exact same thing if you did negative x squared plus 2x minus the cubic function. But since we already did this whole distributing and combining like terms, it's easier to just take what we had above and change the sign. So here we're going to have negative 3x cubed plus 12x. Now I'm going to erase this bounds and integrand work so that there's room to evaluate this integral, but I encourage you to pause the video and work through the antiderivative steps on your own. So if I find the antiderivative here, I'm going to get 3x to the fourth over 4 minus 6x squared from negative 2 to 0 plus negative 3x to the fourth over 4 plus 6x squared from 0 to 2. And if we plug this in and simplify down, we're going to get 12, and I'm just going to write that there to save us a little bit of time so that we can spend some time on some more examples. Okay, let's look at some more examples. All right, so for number 3, we need to graph sine of x and negative cosine of x, at least between negative pi over 4 and 7 pi over 4. We need to figure out where they're crossing and how many areas that is, and then set up the integral and find the area. So let's go ahead and jump into this. I encourage you to pause the video and graph sine and cosine on your own. And if you're really struggling with that, I'm going to help you out. So, sketching sine and cosine, remember that you can always think about the unit circle and use those 4 points on the unit circle. 1, 0, 0, 1. Let's make that readable. 0, 1, negative 1, 0, 0, negative 1. And the fact that every ordered pair is cosine x sine of x. So sine of 0 is 0. I'm going to make these go by pi over 2s. And I know I'm going to have to make my graph go negative eventually just to meet the requirements of the bounds that they gave us in this problem, but I'm going to just start by sketching sine. So sine of 0 is 0. Sine of 1, sine of pi over 2 is 1. If we come over here, sine of pi is the y value of that point, which is 0. Sine of 3 pi over 2 is negative 1. And sine of 2 pi is back up here, which is 0. So we can connect our sine curve here. Now, if we're going to just keep going to make the graph keep going, sine of negative pi over 2 would come back down. So we have our curve for sine. Now, if we're going to graph cosine of negative cosine of x, so now we're going to look at all of the x coordinates and we're going to take the opposite sign since we're graphing negative cosine. So cosine of 0 is positive 1, but we're going to graph negative 1. Cosine of pi over 2 is 0. Cosine of pi is negative 1, but we're going to change it to make it positive since we're looking at the opposite of cosine of x. Cosine of 3 pi over 2 is 0. Cosine of 2 pi is 1, and then we make it negative. So we're going to connect our cosine curve, ooh, hopefully a little bit more carefully than I just did. And we're going to extend it, whoops-a-daisies, there we go, so that it goes all the way to negative pi over 2. So something that I want you to notice here is that we actually have 2 areas. We have this blue piece of area, which I'm going to call A, and we have this green piece of area, which I'm going to call B. That means we're going to need how many integrals? We're going to need 2 integrals, which also means that when we find the bounds, we need to find 3 points that they intersect in. Well, we actually already know 2 of them, but let's pretend that we didn't know that. We're looking for when does sine of x equal negative cosine of x. Well, sine and cosine are the same at all the pi over 4s. We're going to look at the ones where we're looking at x and y being opposite in sign. So that would happen here, which is 3 pi over 4, or down here, which is 7 pi over 4, or negative pi over 4. So x equals negative pi over 4, 3 pi over 4, and 7 pi over 4. And then we can go ahead and set up our first integral. So I'm going to use, this is going to be our integral for a, negative pi over 4 to 3 pi over 4. And what area are we looking at here? We're looking at the area where the red graph is on top for this blue piece over here. So that's going to be sine of x minus negative cosine of x. So sine of x plus cosine of x. Plus the integral from 3 pi over 4 to 7 pi over 4. And here it's switching. So this is going to be the green area, which is going to be negative cosine of x minus sine of x dx. Oops, squeeze a dx here. I'm going to make my life a little bit easier here, and I'm actually going to, in my second integral here, I'm noticing everything here is negative, so I'm going to just factor that negative out. 7 pi over 4. That way both of my integrals are actually the same. And actually I'm even going to rewrite them in the same order. Sine of x plus cosine of x. So my antiderivatives are going to be the same. And I won't have to deal with as many negative signs. You're going to get the same answer even if you leave it as negative cosine of x minus sine of x. This just might simplify things a little bit. So when we integrate, the integral of sine of x is negative cosine of x. The integral of cosine of x is sine of x. And we're evaluating this from negative pi over 4 to 3 pi over 4. And then since I switched the sign here, I'm subtracting, but I'm going to have the same antiderivative. So negative cosine of x plus sine of x but for our second integral, from 3 pi over 4 to 7 pi over 4. So all of our values for sine and cosine are going to be some form of root 2 over 2. So negative cosine of 3 pi over 4 is right here. That's going to be negative root 2 over 2, but then I'm changing the sign, so it's going to be positive root 2 over 2. Sine of 3 pi over 4 is already positive root 2 over 2. Minus, if I plug in negative pi over 4, negative pi over 4 just means I move down here. So I'm in this quadrant where cosine is positive and sine is negative. So minus negative root 2 over 2, because I need to take the opposite of the sign, minus root 2 over 2. I'm going to do the second set over here in a different color. Minus cosine of 7 pi over 4, which is down here, is going to be positive root 2 over 2, but this is going to make it negative. Plus, sine in that quadrant is already negative, so minus root 2 over 2. Minus, if I plug in 3 pi over 4, cosine is negative, and then I have this negative sign, which is going to make it positive root 2 over 2. And then sine is positive root 2 over 2. Sort of feels like an April Fool's joke here with all of these different root 2's over 2. So this right here, root 2 over 2 plus root 2 over 2 is 2 root 2 over 2, which is just root 2. Minus, same thing here, except it's going to be negative, so minus negative root 2 or plus root 2. Minus, over here, I'm going to have this whole thing is going to become negative root 2, and this whole thing is going to become minus root 2. So I basically have root 2 plus root 2 plus root 2 plus root 2, which is 4 root 2 units squared. So the one thing I really like about this problem is it gives us the chance to talk about graphing sine and cosine. It gets us the chance to practice using our different values on the unit circle. So it reviews a lot of the trig stuff that many people are uncomfortable with while tying in the new content. What I want you to remember is if you were just able to set up the integral, you have done the calculus part of what we're working through. Let's look at a few more examples. All right, for number 4, I want to remind you how to graph functions of y or equations that are in terms of y. You can just remind yourself that these are just x equals equations instead of y equals equations. So x equals 4y to the third and x equals y. Well, x equals y is just the same exact line as y equals x. So I'm going to just do a quick sketch of that line. X equals 4y cubed. Anytime you don't remember how to graph something, just make a table. The difference here is that we're going to plug in numbers for y, since this is 4y cubed, and then we're going to find x. So if I plug in negative 1 for y, 4 times negative 1 cubed is negative 4. 4 times 0 is 0. 4 times 1 is 4. And now I have 3 xy ordered pairs that I can graph. So 1, 2, 3, 4, negative 1, 0, 0, 1, 2, 3, 4, and up 1. So this is a cubic function, so it's going to curve. It looks like from my graph that we're going to have 2 areas, and my graph is not perfect. It's much easier when we have axes created for us, but that's not always the case. So let's talk about the bounds. If you can tell from your graph what the bounds are, that's great. Use that. Otherwise, you can algebraically set the 2 functions equal to each other and solve for your bounds. So I can factor out a y here. This is going to give me, if I factor y equals 0 and plus or minus 1/2. If you just solve 4y squared minus 1 equals 0, 4y squared is 1, y squared is 1/4. So you can square root both sides to get plus or minus 1/2, in case you were wondering where that came from. So 3 bounds means I'm going to have 2 integrals. So I'm going to have the area with respect to y plus another area with respect to y. And what are those bounds going to be? Well, the first area is going to go from -1/2 to 0, and the second one from from 0 to 1/2. For the first one, remember that if you can't tell which area is on top, that you can always plug a number in. So you could plug in a number between 0 and -1/2, or a number between 0 and +1/2 to figure out which function is going to be on the top. So for the first integrand, the cubic function is going to be on top and the line is going to be on the bottom. If you plug in something like -1/4, you'll see that the cubic function is a smaller negative, or is a larger number because it's a negative number that's smaller. So this is going to be 4y cubed minus y, and this is going to be the opposite of that, -4y cubed plus y. And I'm going to just do one more step and then tell you what that final answer is so that we don't spend an extra 10 or 15 minutes on this video just doing review stuff. This would give us y to the 4th minus y squared over 2 from -1/2 to 0. And this would give us negative y to the 4th plus y squared over 2 from 0 to 1/2. And because we get to plug in 0, this actually ends up simplifying pretty nicely to be 1/8 units squared. So I do encourage you to go back and work through actually substituting in those limit bounds, 0 and -1/2, 0 and 1, so that you can confirm that you can do the old part of this lesson, or the part that we've been doing all semester, to get down to this final answer. All right, let's start with another example. Okay, number 5 here, we're given the graph, so we're going to use that and not spend some time graphing here to find the area bound between these two curves, which you can see shaded as area A. So the very first thing we're going to do is figure out what the bounds are. Even though that graph looks pretty good, I'm having issues being able to tell what that graph, where it's crossing. So I'm going to set the two functions equal to each other. Now, all of these fractions here are making this problem a little hard to look at, so I'm going to multiply everything on both sides of the equation by 2x so that I no longer have any fractions to worry about. Then I'm going to get everything on the same side, and I have a quadratic that I'm going to solve by factoring. This is going to give me x equals 1/4 and x equals 2. Now I can go ahead and set up my area integral. Now, based on the graph, it looks like the line is the top area and the 1/x, the rational function, is the bottom area. So I'm going to say the integral from 1/4 to 2 of -2x plus 9/2 minus 1/x dx. And then we're going to go ahead and integrate. I am going to work through this one because it has 1/x in it. I want to make sure we remember how to integrate that. -2x is going to become -x squared over 2. Nope, -x squared, right, because the 2 divides out, plus 9/2x minus the integral of 1/x is ln of the absolute value of x, and we're evaluating this entire thing from 1/4 to 2. If we plug in 2, we're going to get -4 plus 9 minus natural log of 2. I can drop the absolute value because 2 is positive. This minus, if I plug in 1/4, I'm going to get -1/16 plus 9/8 minus natural log of 1/4. And this could be simplified more. All I'm going to do is just tell you that if you simplify, if you find a common denominator and simplify the numbers that don't have ln, or that don't have natural log, you get 63/16. And you could either leave this as minus natural log of 2 plus natural log of 1/4, or you could, if you want to, condense this to be natural log of 1/8. But I am fine with you leaving your answer just like this with units squared. Okay, for our last two examples, we're just going to focus on the setup, and I'm really going to encourage you to try and do these last two problems on your own once I get them on the screen. And I'll tell you what the final answer is, but I don't want this video to run any longer than it already has, so I don't want to spend too much time on the integration. So here are our last two problems. I also want you to see if you need to graph in order to integrate this. You can sketch a graph if you need to, but if you can find a way to do this without sketching a graph, that is going to save you time. So go ahead and pause the video, work through 6 and 7 on your own, just getting them to the point where you have the integral that you would use to find the area set up. So here we go. I have drawn a quick sketch for number 6. And I've calculated the bounds, which I could actually see from my graph, but I also just set them equal to each other so that I could find that algebraically. Now remember that when we're finding the area and we have equations that are in terms of y, where y is our variable, we're not looking top minus bottom, we're looking which is the furthest right minus left. So the furthest right is negative y squared plus 1, and then technically we'd be subtracting 0, but you obviously don't need to write that. And then you'd have dy. If you integrate this, you just get negative y cubed over 3 plus y from negative 1 to 1. And if you actually substitute in and simplify, you should end up with 4/3 units squared. All right, last but not least, number 7. So if you do a quick sketch on number 7, you should see that our equations cross twice, so we're going to need to have 2 area integrals. And if we find the bounds by setting them equal to each other, now my graph, I can tell that the bounds are going to be 0, 1, and 2. If you didn't graph, or if you couldn't tell that, then you're actually stuck solving this, which means you're going to need to cube both sides, which means you have to multiply x minus 1 times x minus 1 times x minus 1, or use Pascal's triangle to simplify. This is going to be x minus 1 equals x cubed minus 3x squared plus 3x minus 1. And I'm going to skip ahead a little bit. If you get everything on the same side, you can factor this and solve to get x equals 0, 1, and 2. So we're going to have 2 area integrals, one that goes from 0 to 1 with respect to x, and one that goes from 1 to 2 with respect to x. Again, my graph, I can actually tell which is on the top and which is on the bottom, but if you couldn't, plug in something between 0 and 1, like 1/2, plug that in here, and plug it in here and see which one is bigger. The line is going to be bigger, so this is going to be x minus 1 minus, and I'm going to rewrite this as to the power of 1/3. Because if we were going to integrate it, it's easier to do that when I have the rational exponent. That means that my second integral, the cubic is on top, or I should say the cube root is on top. So that would give us this integral here. Now, just as a reminder, when you're integrating something like this, you can still use the power rule. The derivative of the inside function is 1, so you can just add 1 to the exponent, which would make it x minus 1 to the 4/3, and divide by 4/3 or multiply by 3/4. So that's how you would integrate this piece on both of them, whether it's positive or negative. I just wanted to kind of refresh your memory there. You could also use U substitution if that made you feel a little bit more comfortable. So the final answer on this last one actually simplifies down really nicely to be 1/2 units squared. So key idea in this section, first we talked about problems like number 6, where we have area between 2 curves being formed with equations that are in terms of y is the variable, and how we're looking at right minus left instead of top minus bottom when we're doing that. And then we also looked at what happens if we have functions that cross more than once, or I should say that form more than one area. Then we need an integral to set up each of those areas. So go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.